Right, we're still on the chapter of thyristors. The next section, section 11.5, deals with the silicon controlled switch or SCS. Again, in our books, introductory paragraph you can mark. Remember, this whole chapter is just an introduction to some of these new devices. We're not going into much depth. The silicon control switch, SCS, is similar in construction to the SCR. The SCS, however, has two gate terminals, the cathode gate and the anode gate. The SCS can be turned on and off using either gate terminal. Remember that the SCR can be only turned on using its gate terminal. Normally, the SCS is available in power ratings lower than those of the SCR. Alright, I have to know the symbol, of course, of the device. As we can see there, it has two gate terminals. Basic operation, as on page 571. An SCS is a 4-terminal thyristor that has two gate terminals that are used to trigger the device on and off. As with the previous thyristors, the basic operation of the SCS can be understood by referring to the transistor equivalent as shown in the figure 1134, as we've discussed with all the previous thyristor devices, as it said here. To start, assume that both Q1 and Q2 are off, and therefore the SCS is not conducting. A positive pulse on the cathode gate drives Q2 into conduction, and this thus provides a path for Q1 base current. When Q1 turns on, the collector current provides base current for Q2, thus sustaining the on state of the device. Alright, the SCS can also be turned on with a negative pulse on the anode gate as indicated in figure 1134A. This drives Q1 into conduction, which in turn provides base current for Q2. Once Q2 is on, it provides a path for Q1 base current, thus sustaining the on state. To turn the SCS off, a positive pulse is applied to the anode gate. This reverse biases the base emitter junction of Q1 and turns it off. Q2 in turn cuts off and the SCS ceases conduction as shown in figure 1134B. The device can also be turned off with a negative pulse on the cathode gate as indicated in part B. And also to mention here, the SCS typically has a faster turn off time than the SCR. Right, there are the figures with the BJT circuits with the gates as pulses as shown, and the device switches on and off as indicated. Alright, just below figure 1134 there is also another method of turning off an SCS. In figure 1135 A and B shows two switching methods to reduce the anode current below the holding value. In each case, the bipolar junction transistor acts as a switch to interrupt the anode current. Now, this should look familiar also to the methods that we've discussed previously with, I think it was with the SCR. Remember, these devices keeps on conducting as long as the anode current remains higher than the holding current. So I have to get the anode current lower than the holding current. So what is going to happen in this case? Oops. With this pulse on the BJT, the transistor is going to switch off, and of course the current is interrupted, no current flows, and the device will switch off. So similar to the one that we've discussed, which was the anode current interruption. That was the name that was used with the SCR. And this method Should also look familiar, although a different device was used. The transistor in this case, if I switch the transistor on, I am relaying the current in that direction. So the current follows the easiest path. The anode current becomes lower than the holding current, and the device also switches off. Now, what was that method called again with the SCR? Although it used a different device. Forced commutation sort of stuff. Now, remember the other method we discussed was forced commutation, where I forced the current in the opposite direction of the anode current, and the device also switched off. All right, back to the textbook applications. Last section there. The SES and the SCR are used in similar applications. The SES, however, has the advantage of faster turn off with pulses on either gate terminal. However, it is more limited in terms of maximum current and voltage ratings. Also, the SES is sometimes used in digital applications such as counters, registers, and timing circuits. All right, this also then concludes this section. And as I've said, you have to be able to explain just the basic operation, know the symbols, and perhaps some of the applications discussed.